Hey everyone, it's Dr. Garner here. In this video, we're going to look at how electrons are arranged within atoms. The arrangement of electrons around the nucleus is described by quantum mechanics, and the quantum theory of electrons tells us a couple of important things. The first feature here is that the energy levels of electrons are quantized. What that means is that only specific energies are permitted, whereas other energies are not allowed. So electrons are also organized according to their energies into sets that are known as shells. These different shells of electrons have what we call an n quantum number or an n value associated with them. So each shell is given a number. So the n equals 1 shell would just be the first shell, and then we could just count up from there. Each shell of electrons is going to have a different energy. So the higher the n value, the higher the shell number, the higher the energy electrons will be when they're in that shell. And they're also going to be further from the nucleus. So higher shells of electrons are further and further from the nucleus, at least on average. So I don't want to imply here that shells have fixed distances from the nucleus, but on average, electrons that are in higher shells will, on average, be further from the nucleus. And we can rationalize this dependence on energy and distance using Coulomb's law, which we saw introduced a few videos ago. So when we learned about Coulomb's law, we saw that whenever we have oppositely charged particles, like say a positive nucleus and a negative electron, the lowest energy state we can have is when those two particles are close to each other. As the distance between them increases as we pull them apart, their electrostatic potential energy will go up. So as we go from the state where they're close together to one where they're far apart, we go from a state of low energy down here up to a state of higher energy up here. So as we move further from the nucleus, as we go further away to these higher shells, we're going to go towards higher energy as well. So our lowest energy shell of electrons is going to be the shell that's closest to the nucleus. If we take an electron from that first shell and move it to one that's further from the nucleus, we're going to be in a higher energy state because we've moved a positive charge away from a negative charge. All right, shells of electrons are further subdivided into units known as subshells. So the subshells are labeled in order using the letters S, P, D, and F. So different subshells of electrons have different shapes to them. So these different subshells have different shapes according to the volume of space in which electrons are found that are part of that subshell. So for example, S subshells have a spherical shape. So electrons that are part of an S subshell are found in a spherical volume of space. With P subshells, they have sort of a dumbbell shape. So electrons that are part of a P subshell, they occupy a volume of space that's shaped kind of like a dumbbell. D subshells have a cloverleaf shape to them. F subshells have kind of complex shapes to them, so we won't go into those in this course. So these subshells tell you something about the shape of the volume of 3D space that an electron resides in. And different shells have different numbers of subshells. The number of subshells within a shell is always equal to the shell number. So for example, the first shell, which has this n of 1, shell number 1, is going to contain one subshell. Shell number 2, the second shell, is going to contain 2 subshells. So whatever the shell number is, that's how many subshells there will be. So as you might guess, the third shell would therefore have 3 subshells that are part of it. The subshells that are present are always kind of in this order. So there's always an S subshell. If there's a second subshell, it will be a P subshell. If there's a third subshell, it will be a D subshell. If there's a fourth subshell, it will be an F subshell. All right, so that means the first shell, with its one subshell, only contains an S subshell. It does not contain any of the others. The second shell, which contains 2 subshells, would contain an S and a P subshell. The third shell, which contains 3 subshells, would contain an S, a P, and a D subshell. You'll often see these subshells labeled using the formalism that we see here, in which we have a number, like in this case 3, followed by our subshell symbol, so 3S. This number in front of the letter represents the shell number. So this is the S subshell that's part of the third shell. 3P would represent the P subshell that's part of the third shell, and so on. So different subshells are also able to hold different numbers of electrons. The S subshells can only hold 2 electrons. P subshells can hold up to 6 electrons. D subshells can hold up to 10 electrons. And F subshells can hold up to 14 electrons. So we have a practice problem here to try out. Here we're being asked how many electrons can the second shell hold. Again, as always, I would encourage you to pause the video and try this problem out on your own first, and then we can take a look at it together. All right, from this slide, we can see that the second shell contains the 2s and the 2p subshells. So we know the 2 subshells that are present. And from over here, we saw that s subshells hold 2 electrons, and we saw that p subshells hold 6 electrons. So in total, the second shell must hold a total of 8 electrons. So 2 plus 6 gives us a total of 8 electrons in the second shell. So that's going to give us choice C here as our answer. All right, so on this slide, we're going to take a look at how to write out the electron configuration of an atom. The electron configuration of an atom describes the subshells that are occupied with electrons. So they tell you where the electrons in an atom are located in terms of the subshells in which they reside. Generally speaking, electrons are going to occupy lower energy subshells first. So these different subshells have different energies associated with them. And they're listed out here. So the lowest energy subshell is the 1s subshell. And if we work towards higher energy, the 4p would be on the higher end. And there are, of course, subshells beyond this as well, but this is as far as you need to know in this class. Now, they kind of go in the order that you might expect. We start with our first shell and do the s subshell first. Then we go to the second shell, do the s first, and then p. Then we go to the third shell and do s, p. And here's where things get just a little funny. The 4s and the 3d are flipped relative to what you might have expected. It turns out that the 4s subshell is just a little lower in energy than the 3d subshell. So we tend to fill it with electrons first before filling the 3d subshell. So that's really the only thing here that's a little bit tricky. All right, so higher energy subshells, we fill them only after the lower energy ones are filled to capacity. So for example, we would start by filling the 1s subshell first. It can hold up to 2 electrons, so if we have more than 2 electrons, we would need to put those in the next lowest energy subshell. So the 2s could also hold 2 electrons, so if we have more than that, we would then need to proceed to the next subshell and so on. If you forget the order of these subshell energies, there's actually kind of a scheme that you can use to remember this. So you can draw out a diagram that looks kind of like the one that I have here, in which each row in this diagram represents a different shell number. So we have the n equals 1, n equals 2, and so on for each shell. And each column represents a subshell symbol. So here this is the S, this is the P, D, F. All right? Then what we did was we just connected everything with these arrows, these diagonal arrows. And if you're wanting to know the order of the subshell energy, just start with that top arrow and follow it from its beginning to its end. So we go through 1s first, right? So that's consistent with what we have up here. Then jump over to the next arrow and go through 2s next. Then we'll jump over to the next arrow. Then we'll go to 2p and then 3s, so that's consistent as well. Then jump to the fourth arrow. We go through 3p and 4s, so that's consistent. And then jump over here and we go to 3d, 4p, 5s, so that's consistent and actually goes a little bit beyond what we showed up here. So if you ever forget the ordering of these subshell energies, you can always use this as a mnemonic for coming up with that again. All right, so let's actually write out some electron configurations. Let's start with the simplest example, hydrogen. So hydrogen only has 1 electron. So as you would imagine, it's going to occupy that lowest energy subshell. So it's going to go in the 1s subshell. The notation that we're going to use to show this looks something like this. We're going to show the subshell symbol, so 1s, and then we're going to follow it with a superscript showing the number of electrons that are found within that subshell. So the electron configuration for hydrogen would be 1s1, indicating that there's 1 electron that's found in the 1s subshell. If you wanted to write electron configurations for other elements, we would just continue to add electrons. So for example, for helium, helium has 2 electrons, so we would put that second electron also in that lowest energy 1s subshell. So for helium, its electron configuration would be 1s2, indicating that there are 2 electrons in the 1s subshell. We could keep going. If we do this for lithium, lithium has 3 electrons. So again, we would put the first 2 in the 1s subshell, but then that would fill up the 1s subshell, so the third one would have to go into the next lowest energy subshell. So if 1s is filled, we would progress to 2s. So that would give us 1s2, 2s1. So that means that there's 2 electrons in the 1s subshell and 1 electron in the 2s subshell. We could keep going if we did this for beryllium. Beryllium has 4 electrons in total. So we would put 2 of them in the 1s, just like we've been doing, and then the other 2 would go in the 2s subshell. So we would end up with 1s2, 2s2. If we moved over to boron with its 5 electrons, we would just, again, start with what we had for beryllium, but we just need to add 1 more electron. Both of these subshells are filled, so we'll need to progress to the 2p next. So it's going to give us 1s2, 2s2, 2p1 as our electron configuration there. Now, as you can imagine, these can get pretty cumbersome if you're writing out electron configurations for elements that have a lot of electrons. So we have a scheme that we can use for abbreviating these electron configurations. And these are based around the electron configurations of the noble gases. So for example, neon, which is a noble gas, in column 8 on the far side of the periodic table, it has an electron configuration of 1s2, 2s2, 2p6. So what we can do is we can abbreviate all of this stuff that is associated with neon's electron configuration. You can abbreviate this with just a symbol. So instead of writing out all of this when you write out an electron configuration, oftentimes you'll just put a symbol for a noble gas with brackets around it. Say, for example, if I wanted to write out the electron configuration of sodium, I could do that the way that we've been describing. That would give us 1s2, 2s2, 2p6, 3s1. But if I wanted to abbreviate that, I could just take everything that sodium has in common with neon, and instead of showing all that, I can just show the symbol for neon with a set of brackets around it. So my abbreviated version of sodium's electron configuration would be neon 3s1. And everything that comes after this noble gas configuration, these are known as the valence electrons in this atom. Everything that's abbreviated by the noble gas, these are known as the core electrons. So valence electrons are the outer shell electrons. These are the outermost electrons, so the electrons that occupy the outer shell of that particular atom. They're the things that, again, come after the noble gas abbreviation. The electrons that are abbreviated with the noble gas, these are known as core electrons. These are the inner shell electrons. They occupy the interior shells of a particular atom. All right, so we can do this for other noble gases as well. We don't have to just use neon as our abbreviation. So for example, argon, which has this electron configuration that I'm showing here, you could write that instead using your abbreviation for neon, or you could just simply abbreviate all of this using this symbol for argon here. So then if you wanted to say, write the electron configuration for potassium, instead of only abbreviating the stuff that it has in common with neon, now I can abbreviate everything that it has in common with argon. So the electron configuration for potassium would be argon 4s1. So for potassium, this 4s electron is its 1 valence electron. Everything that it has in common with argon, those are its core electrons. All right, the periodic table is organized according to electron configurations. So you can use the periodic table to make writing these electron configurations much easier. So the first 2 columns of the periodic table, these are known as the S block. Atoms that are in this region of the periodic table in these first 2 columns, their highest energy occupied subshell is going to be an S subshell. So the highest energy subshell that's occupied with electrons would be an S subshell. Same thing over here on the right with these elements that are shown in green. This is known as the P block. So the elements in the P block, their highest energy occupied subshell is going to be a P subshell. So their valence electrons reside in that P subshell. Everything in the middle, the transition metals, their highest energy occupied subshell is going to be a D subshell. Everything down here in these 2 rows at the bottom of the periodic table, these are the F block elements. Everything in the F block is going to have an F orbital as the highest energy occupied subshell. I also want to point out that if you have 2 elements that are in the same group or the same column, they're going to have the same valence shell electron configuration. So for example, if I have, carbon would be here. So if I had carbon versus silicon, both carbon and silicon would end up having 4 valence electrons. So everything in the same column would have 4 valence electrons. Everything in the next column would have 5 valence electrons, and so on. All right, so let's try out a problem here. We're being asked how many valence electrons are in a sulfur atom. Again, I would encourage you to pause the video and try this out on your own first, and then take a look at the solution together. All right, so we're trying to figure out how many valence electrons are in a sulfur atom. So it would make sense to start by writing out the electron configuration for sulfur. So we could start by knowing the atomic number of sulfur, which is going to tell us how many electrons we need. So sulfur's atomic number is 16, so therefore it must have 16 protons. And if it's a neutral atom, the number of protons and electrons is going to be the same. So our neutral sulfur atom would also have 16 electrons. So that's how many electrons we need to place into subshells. We can go ahead and start by showing the periodic table here, and we can use this as a guide for how to write out this electron configuration. We're going to start at the beginning here. So the first subshell that we're going to fill with electrons is the 1s subshell. And as you can see here, there are only 2 spots on the periodic table, consistent with the fact that it holds 2 electrons. So we'll put those first 2 electrons in the 1s subshell. You'll notice over here I circled sulfur, so you can see where we're trying to get to on the periodic table. All right, so the first 2 electrons go into the 1s subshell. If we kind of follow this down to the next row, 2s comes next. So the next 2 electrons go into the 2s subshell. If we keep going, 2p comes next. P subshells hold 6 electrons. So the next term that I'm going to have here is 2p6. If I jump down to the next row, I have 3s, and it holds 2 electrons. So my next term here is 3s2. If I jump over to the next section, we have 3p. It holds a total of 6, but we only need to put 4 in it to bring us up to a total of 16 electrons. So we end up with 3p4. So we've placed all 16 electrons now. We had 2, 4, 10, 12, 16 that we've placed. All right, we could think about this in terms of a noble gas abbreviation as well. So everything here, these first 3 subshells, these are all common with neon. So we could abbreviate the electron configuration for sulfur as being neon, 3s2, 3p4. So remember, everything that comes after the noble gas abbreviation is a valence electron. So these 6 electrons here, the 2 that are in the 3s and the 4 that are in the 3p, these are our 6 valence electrons. So sulfur has 6 valence electrons. I want to show you a shortcut for this as well. It's a little hard to see on the periodic table that I'm showing here, but the periodic table that you'll have on exams and that you'll often see in a lot of places will have the group numbers for these columns listed in a format that ends in either the letters A or B. For example, if you were to look at sulfur on the periodic table that you'll have on the exam, you'll see that it's in column 6A. That 6 tells you how many valence electrons there are. So the group number tells you how many valence electrons a particular element would have. So anything in column 6A would have 6 valence electrons. All right, so our answer here was 6. All right, we'll stop there for this video. Thank you for watching.